Well, thank you, everyone. Appreciate everyone's time this afternoon, and really happy to be here today. My name is Jeff. I'm a senior product manager on machine learning. And so Unity does a lot of things in machine learning. So today we're going to talk about a couple of the interesting projects that we have going on. Specifically, Unity machine learning agents. So we'll talk today what that means in this project that we've been working on, and kind of what that means from a game development perspective. Okay, maybe stand here. Okay. So before we start with what machine learning agents is, we really have a really simple question: is that can we design machines to learn? And what do we mean by that? So I'll give you an example of think about an appliance you have at your home. It could be like a coffee maker. So how does a coffee maker work today? You go in, you put the grounds in, you hit a button. 30 seconds later, the water starts to drip, and you get a cup of coffee. Now imagine, the coffee machine can observe your behavior. Maybe you're a little bit tired today, and so the coffee maker makes it just a little bit darker. Maybe that you're in a hurry, so it puts a little bit cooler water in there so you don't burn yourself. Now think about having to design machines that take all these different millions kinds of palettes and how long it would take to actually code those. So this is really the premise of machine learning agents, is that instead of coding everything by hand, all the tasks and all the behaviors, we're going to design the machines to learn. And then we can show today kind of how that works in the game development case. Okay, so teaching machines to learn in a game, we think there's really three primary use cases. The first one is behaviors of NPCs. So things like combative or cooperative players in the game. So it could be somebody you're shooting against, somebody that's playing along with you. The other side we think about when we teaching machines to learn is in testing. Could we design a machine to find really, really difficult bugs in the game? Or could we test the game to find impossible situations the player could be in? And the third one is around game design. So think about, is this level too hard? Right? Can the agent figure this game out in 30 seconds? Did it take them, 1 month to figure it out? So these are kind of three areas we think that machine learning can really help, especially in machine learning agents in game development. And so this is what I want to introduce what machine learning agents is. Today, it's our solution to kind of address this behaviors in games. It's an open source project on GitHub today. We're actually a top 25 project for AI. We're kind of we're based in Silicon Valley, so we have a lot of people are in this space and trying to either in gaming or in simulations. And so today that's where the project sits today. So anyone in here, we'll have some slides later. You guys can go and download it, kind of play around with your games and your Unity scenes, and it works, really well with Unity. So before, this is a little bit small, but what are agents? And I want to define that before we kind of go into, kind of the presentation, just to set the expectation of what that is. So agents perform the acts and are embedded within a scene. So this can be anything inside of a game that does something. At any given moment, agents are in a certain state. From the state, agents can take a set of actions. And every time they take a set of action, it brings them to a new state. And they either get some sort of negative or positive reward. And then what we think about as a policy is used by agents to determine those actions. Now, with this, we can teach the agents over and over again to learn the right behaviors to maximize what we call the cumulative reward. So just to kind of recap these definitions. An agent, again, it performs the acts in a scene. The state, the full or partial observation of the scene from the agent. So the agent, let's say I'm a player or a character in the game. I can see the game, that's what the state is. The actions, what the agents can do to move from one state to another. So if I'm a player, I can walk forward, I can walk back, I can crouch, I can jump. Any of the actions that characters are allowed to do in the game. Policy is how the agents determine which actions to take, and we'll talk a little bit more about what that means. And then the reward is the value gained or lost where the agents move to a different state. So these are some very, very basic terminology. I just want to kind of set that before we talk a little bit deeper. So what do we need to teach agents to learn? The first thing is we actually need very compelling game levels and scenes. So from a research and machine learning perspective, Unity is a really, really great platform to do something like this. You need some sort of visual complexity. What I mean by that is just really, really rich views of the world. If you think about ourselves, we can see into the world, we see all these beautiful mountains, we see all these beautiful landscapes, and That's kind of one component you need to train agents. The second one we call is like physical complexity. So if you think about things like your joints, things about falling down, think about the physics of the world. When you have an agent in a game, it needs this sort of understanding of the physical complexity. The last one is what we call cognitive complexity. Agents also need a somewhat difficult problem to solve, and especially in gaming, where games are meant to have some level of difficulty. And so we think these are the kind of three pieces in the scenes and levels to design really great agents. So we also need, to train agents, you also need training methods. Now today we're going to talk about two, reinforcement learning and imitation learning. We'll go a little bit deeper in what these means in the later sections. So how does Unity fit in? Whoop. Oh, no worries. Cool. All right, switcher. Okay, cool. All right, we got a clicker that works. So how does Unity fit in? Oops, wrong way. The Unity ecosystem. So if you think about Unity, every day there are thousands of games being shipped all over the world. If you think about the physical complexity, the visual complexity, and the cognitive complexities, Unity has it all. It has this gigantic ecosystem of really great ways to train agents. So in a lot of ways, Unity is just a great way to design these agents, especially in the gaming world where there are all these different kinds of scenarios. So this is kind of where we get into like the meat of this, right? So kind of talk about what training agent means and some very, very high level details. So how do we actually train them and use them in games? So that's probably the question that most developers always ask us when we talk about this topic. So this is the kind of workflow we envision. Again, this is just kind of how it is today. We're always looking to improve it, trying to make it easier for game developers to do this stuff. But first thing is that you have to set up a game. And you have to set up the game for training, and that means maybe there's a specific level or a specific scene. The second part is you actually have to train the agents. Now today, we use what's called Google TensorFlow. It's just one of many packages you can use that are open source to train agents. Now we happen to use Python and TensorFlow, but if you use PyTorch, any other libraries, it works with ours as well. And then the last part, which is always the most challenging, is taking the brain and putting that back into the game. And we'll talk a little bit how that kind of is done as well. So setting up the game for training. So this is a very simplified model of how this works. So I'll kind of start from top and go down to the bottom. So at the very top, we have what we call the agent. Now, if you're familiar with Unity, this could be a character. This could be a wheel on a vehicle. This is basically anything inside of a scene that can do something. Now, again, it doesn't have to be a character itself. It can be other objects, but anything that has a certain kind of action in the game. And then what's connected to the agent is what we call the brain. Now, the brain basically dictates how the agent behaves and what it can do. So, for example, let's say I'm a wheel on a car. I can turn left, I can turn right, I can go forward, I can go back. The brain is really what determines what the action that the agent takes. And lastly, what we call the academy. The academy has two parts. Academy is actually what trains the brain. So the brain, just out of the box, doesn't really know anything, doesn't really do any actions. The academy is what actually trains the brain to do it. And then from the academy, what we do is we created a lot of external communicators to Python. So for those who are familiar with machine learning or have done machine learning projects or are machine learning practitioner, you know that the whole world lives basically in Python. And then if you're a Unity developer, you know that the whole world lives in C# and you're building scenes. Very, very different world. So what this academy does is actually bridge the world between the Python machine learning side and Unity. And this is what you need to do to set up in a level to actually train agents inside. Again, we'll have some cool demos and examples of how this actually works. But this is just kind of how we set up the game for training. So speaking of that, now we think about how do we train agents. So we have a scene, everything's set up, everything's connected, we have all the wiring. So let's think about how we train. So we talked about two different training methods. The first one we'll talk about today is reinforcement learning. So what is reinforcement learning? Agents learn through rewards. A lot of trial and error happens until the models are optimized and simulations can be sped up quickly. So the way I describe it is that you basically let the agent run over and over and over again, millions of times, thousands of times, until it figures out what is considered correct. There's a movie from Tom Cruise called Edge of Tomorrow that he keeps dying, he comes back, he keeps dying, he comes back, and eventually he becomes a super soldier that's unstoppable. So that's really what the predicated on reinforcement learning. It's just the fact that the agents become very superhuman. So let me just kind of describe that process very quickly. So the first thing is that the agents actually observe something. So let's pretend I am an agent. I'm a character in game. I come down and I observe something in my world. Okay, so what can I do? Now I could take an action. So maybe I walk forward and toward the forest. So I'm walking toward the forest. That's my action. And as I'm walking, I'm either getting some kind of reward, either positive or negative. So for example, if I'm walking in the forest and a bear jumps out and kills me, that's probably a negative reward. But if I'm walking toward the forest and I get, let's say, a pot of gold, then maybe that's a positive reward. And this happens over and over and over in the learning process until the agent actually figures out, what is the most optimal path. And that's what we consider the policy. It kind of starts to explore, so I kind of will walk around, maybe I get killed, maybe I pick up some gold, but over time, I'm going to take a strategy that exploits my environment. And so I will always have an optimal path, during this process. So I'm going to show you a kind of an example here. So it's kind of like, this game is like, we call it chicken crossing the road. So you have, what you can see is you're observing the pixels in the frame. So what can you do? All the things that the chicken can go left, it can go right, it can go up and go down. That's the only actions the chicken can take. And so what are the rewards? Okay, so if it gets a gift box, it gets a positive reward. If it gets hit by a truck, it gets a negative reward. Now I'm going to show you the demo on how this actually works in the actual training. And this is using ML agents to train. So before training, as you can see, the chicken's really just kind of running around, right? Again, this is the explore phase. It's just looking around. It's kind of figuring out what's going on. It's not really great, right? It keeps getting hit and it dies. So what happens after 1 hour of training? Okay, it's getting a little bit better. A little bit better. Still gets hit. A little bit better, but as you can see, just 1 hour of training. Okay, after 6 hours of training, though, this is really, really fascinating. It just crushes it. It just runs right through it. Unstoppable. This is superhuman, right? Now, this is a very simple example, but just 6 hours of going through repeated deaths, getting hit by cars, getting gifts, it's unstoppable. Again, this required no coding. I'm not a great coder. I'm actually years away from coding, and you can see that the chicken can just figure out how to play the game. So we'll talk about kind of the comparison of both. So I'll talk a little bit about imitation learning and how that's different from what we just saw. So what we saw earlier was that the chicken would just continue to play the game. What imitation learning is actually the agents learn through demonstration. So basically, it watches the player play the game and it doesn't take long to mimic the behavior. So human plays the game, the agent is watching how the player plays. You need some real-time interaction. So the agents get trained basically, not in like simulation. It doesn't run it like 1,000 times. It just watches the player play the game, once. And then what happens at the end is what we call human-like ability. Now, again, you saw the chicken, right? The chicken was superhuman. This becomes just sort of regular human. So again, the process works like this. The human's playing the game, and the policy that gets created by the agent is simply just by watching the human play. Again, it's very, very simple. This is probably the most simplistic training method that we have, but that's a very compelling way to build an agent. So I'll also show you a demo here as well. So this is Anti-Graviator, a game that's actually in the market from our friends from Cybernetic Wars. So let me just show you. You have human on the left, agent on the right, or machine on the right, excuse me. So this may be a little loud. Okay, actually no sound. So as you can see, the machine's right now it's kind of learning from the human right now. You see the machine keeps hitting the wall. So in about maybe 5 or 6 seconds, it starts to get the hang of it. It's still hitting the wall, but as you can see it kind of turned a little bit, right? You see it kind of makes this curve just a little bit smoother. It's just watching the player play. So within 25 seconds, it actually figured out how to play the game just by watching the human play. So as you can, this is actually about 30 seconds. You see it actually can make the turn. Starting to smooth out a little bit. And this is just after a few hours. Now it's just running perfectly. So again, another way to create an agent of the game, but it doesn't really require coding, but it's a little bit different from reinforcement learning in that it watches the human play. So we talked about the two training methods, right? There's reinforcement learning and then there's imitation learning. And so what's the difference between both, right? What different use cases is it possible to leverage these two different training methods? So the first one is reinforcement learning. It creates a superhuman-like character, like you saw the chicken. Now, if you're playing a game, and at least for me, I don't want to play a game where my opponent is like a superhuman. I will die in a few seconds. It's just not a fun experience. So, and sometimes you may not want the NPC to be superhuman because it just doesn't really quite make sense. So in some cases, though, if you're testing a game, for example, maybe you do want a superhuman agent. Maybe if you're testing a game, you want something that can just breeze through it really quickly. Maybe you want to know if it's very difficult, it's too hard, or maybe if the superhuman agent can't finish the level, how do we expect a human to actually finish the level? So there's some scenarios where reinforcement learning makes sense. Now think about imitation learning, human-like ability. So if we're playing a game, we probably want to play against people who are like us. They're not going to be superhuman. They play kind of like us at a certain level. And if you think about like adaptive difficulty, if you're playing a game that gets progressively harder or easier, this is kind of one area that these kind of scenarios make sense. So included in ML agents, if you go to GitHub and you download a repo, we include a bunch of starter examples. Now these are very basic Unity scenes, but we include a whole list of them to kind of test different kind of ways to train. Now, this is just a kind of a starter. If you're new to machine learning and you're trying to get into it, this is kind of like a way that we'll provide you assets to actually get started. And we're going to talk about these 4 today. So these are just talk a little bit more about the kind of ways you can train. So, okay, so the first one is this 3D balance ball. This is kind of our first example that our team shipped with. So the goal, right, is that you see there's a platform. And you want to keep the ball on top of the platform as long as possible. Okay, what can the agent observe? All it can do is just watch the platform rotate and sees where the ball position on the platform. And then the actions, all the thing the platform can do is just move. It can just tilt, basically trying to keep the ball up, online. And the rewards is every time it keeps the ball longer on the platform, it gets a positive reward. So what you see happens after about 10 minutes of training, again, this is actually part of a Unity scene. We put the brain back in here. The ball never falls. So about 10 minutes, you can kind of figure out that the ball doesn't move. Now, this is, again, very, very simple example. It's kind of the starter that people can kind of get into to look at the code and kind of get things going. The second one is curriculum learning. Now, anybody here take calculus before? Calculus. Okay, some people take calculus. Okay, so when you take calculus, you don't just learn calculus, you learn algebra first. And you don't just learn algebra first, you learn arithmetic. So same thing when you train agents inside a game. You need this sort of step curriculum to kind of have simpler exercises for agents to learn to take on more difficult tasks. So on the right side, you see that at the very top, the agent's learning very, very simple tasks. As it progresses through the curriculum, it actually learns the very, very difficult tasks. And what you see is this outcome is that this agent can actually figure out how to get over the wall by learning these very, very simple steps first. And it takes a lot, it's faster to train, and it's just a different way of teaching an agent. The second one is, the other one is what we call short-term, long-term memory. Now, this is actually an interesting concept. Have you ever gone inside of a room and you open up the door and you forgot what you just saw a few minutes ago? So that's the concept of short-term and long-term memory. In agents, they have to have this concept like remembering what happened, certain steps ago or certain engine cycles ago. And so part of this is that in this demo, you see that the agent sees that the color orange and it goes to the right one. As it passes the block, it figures out which one to go and it stores that in its memory. Now, in machine learning and also in gaming, this is a very, very, this is a very, very interesting concept because there's long-term and short-term memory, and how do you balance that in a game, and especially within an agent. The last one I'd like to talk about is what we call multi-agent soccer trading. So today we talked quite a bit about just a single agent, just one agent in a game, running around. Now this is the concept when you actually put multiple agents together with different brains. So in this case, you have one soccer player that plays offense. So he's kicking the ball, and all he's learning to do is to strike and hit the goal. You have another agent that's learning to defend the goal. So it's just playing goalie, trying to block the ball from going into the goal. And then you put them together. Actually, they learn to play soccer in a very natural way. So I'm going to show you that real quick. So as you can see, the agents are figuring out how to play soccer. You notice that the goalies don't leave their goal. We didn't program to do that. They learn that defending the goal is the most important thing they have to do, so they stay by the goal. Just like the striker, the most important thing is try to get the ball into the goal. And again, we didn't code any of this. We didn't tell the agents, like, we didn't program a clear path. We didn't program, these specific pieces. They learn on their own to do this. And so that's kind of the premise, like multi-agents. If you put different brains, different agents inside of a game, you'll find very, very interesting behaviors. And if you can imagine, a full soccer player with all the players could be very, very interesting as well. So we talked quite a bit about training. So the last part is like, okay, I've trained my agent. I got, like I figured it out. Okay, this thing works pretty cool. How do I put this back into the game? So this is a really interesting this is kind of where we are trying to push the frontier and boundary of what is possible to embed these models into devices. So today, the way it works is that you train an agent, and what happens is like a file comes out called a bytes file, and this is the models file that actually is the brain of the agent. Now this brain, for a very simple example, could be very small. For a very complex game, it can be pretty large. And so what you do is you take this brain, and we use what's called a plugin today called TensorFlow Sharp. It's a Unity plugin that you takes the bytes file and embeds it into the game as a brain. Now, all of what I'm describing is available in our ML Agents package. So when you download it, you'll see all this stuff, and kind of know how it works. Now, the challenge with this is that running these models on devices can be very expensive. Today, TensorFlow Sharp, for example, only runs on the CPU. A lot of neural networks and a lot of these models that we're training on are run better on the GPU. But as you know, when you build a game, the GPU is basically taken up with graphics and all the parts of the game. So we're trying to figure that out and actually kind of help developers. If they want to build these kind of experiences or these kind of agents in the game, helping them be able to embed these models back into the game. And it's a very, very huge challenge. This is not just a Unity, specific thing. All the device platforms that are running neural networks and these kind of models on devices are facing this as well. Luckily, we are collaborating with different industry leaders. We have Microsoft WinML, which is actually like running machine learning on Windows devices. You have folks like Google TensorFlow Lite and Apple Core ML who are working on solving the inferencing challenges on their devices. And of course, there's other platforms for the future, Nintendo, Sony, and other consoles. Now today, what we believe at Unity is that if you want to create a neural network model or a model for an agent, and you want to work on all platforms, you just can use Unity. We'll kind of help solve these very implementation details for you. That's kind of our vision with embedding these agents in games. But again, today, it's in beta, very experimental. We have seen a few games working with this in some of their pre-production stuff. So it's getting there, but just know that this kind of side it's a very, very complex problem to solve. So kind of where are we headed with all of this? So we kind of talked again about 3 different areas. We have behaviors, NPCs, testing, and design. And all of the use cases we think about in gaming are kind of centered around these areas. As you can see, as you can imagine, we talk quite a bit about behaviors, embedding, different kind of agents in games. There's all host of testing and design things that we can do with reinforcement learning and also imitation learning. So what's included in ML Agents today? We do have this kind of set of core features. You'll get, of course, like all the installation, all the stuff that works with Unity, the Python, documentation, all the examples that you saw, the monitor. We have a Docker image if you don't want to install Python and deal with that. So we have just a core set of a package that you can use today. In terms of training features, we have all kinds of ways. We talked about 4 today in reinforcement learning and imitation learning, but we also have on-demand decision making, adversarial self-play, which also leads to very interesting use cases, and of course cooperative and combative multi-agent scenarios. So again, this is just kind of the stuff that we're kind of shipping today. We're always obviously kind of adding on more and more different ways to improve this experience for all. So again, where are we headed? We want to make it just, again, simple and scalable for all kinds of games. The first one is just making it simplifying the workflow to train agents. Today, you saw that you have to install Python, you have to train, you have to pull all this stuff online. We just want to simplify that, make it really easy to train these agents. a lot of folks in the game community are not necessarily machine learning experts. So we also want to make it you be able to do all this stuff without having to know, all the machine learning, details and aspects. Support to run the agents in the games is a big one. So if you want to run this in a game, different ways that we can help you do that as well. And of course, always adopting state-of-the-art algorithms and the machine learning world and bridging those two worlds together. So with that, again, I really appreciate everyone's time. Again, you kind of listed up our contact, our website. Feel free to shoot us emails. Always happy to hear from game developers on these things. And of course, find us on GitHub. Again, we are all of our stuff's up there. The latest and greatest will be there. So with that, I will open up questions from the monitor. Let's see. Oh, okay, got it. So the first question is, can I create my own environment with ML agents other than examples provided by Unity? Absolutely. You can, using one of our examples as maybe a template to start, you can bring in your own environments and kind of hook this stuff up. Again, we're still in beta, so if you're having some trouble getting your environments to work with ML agents and your scenario, please email us. We have issues. We definitely want to hear from you guys if you're having trouble getting your environments to work with ML agents. Second question, do you have plan to support something other than reinforcement learning, such as content generation, any timeline? So there is another team at Unity that is exploring using reinforcement learning, machine learning to improve the workflow of the game. It could be something like using procedural content generation, creating different kinds of animations that are machine learning driven. Today, our team is mostly focused on behavioral aspects of the game, and there is another team that is looking to bring these techniques into a different lens, especially in content generation. So, what is the difference between Python and TensorFlow with ML agents with TensorFlow Sharp? So TensorFlow is just the way that we use to train the agents. And TensorFlow is just, like PyTorch and these other machine learning libraries, just one way to actually, just what we use to actually do the training. TensorFlow Sharp, which is a plugin, takes a TensorFlow model. So again, you do the training, output is a TensorFlow model, and TensorFlow Sharp takes that and actually basically creates like a C# equivalent for it to run inside of a game. And now, if you think about that, you're taking TensorFlow model, converting it sort of into C#, and it'll work in a very non-performant way. So today, again, it works for certain scenarios, but if you have very, very big models or a lot of latency requirements, those things may get a little bit not as performant with TensorFlow Sharp, the plugin. Could ML agents be used to solve logical problem solving like puzzle games? Say I want to list all the possible solutions and possible moves in each step in a puzzle level game. How would Unity ML be used to achieve this? So absolutely, yeah, for sure. And one thing is that even in a puzzle game or any kind of game, if you want an agent to try to solve it, or if you want to create maybe another player in a card game, it's all about designing the reward function, which is what the if a player makes a certain move in a card game or has a certain event, what are the positive and negative rewards? And also, of course, the designing the states as well. So for a puzzle game, you can see that the states, the observation could be, it'll be a non-visual observation that has a discrete state with a certain reward function that rewards the agent for completing the puzzle in a certain way. So absolutely, there's definitely scenarios that can work. A little bit trickier because puzzle games are always just a little bit tricky with these kind of things, but definitely possible. Do you think ML agents can replace QA team? Very, very good question. There's always going to be a need for human-driven curation and QA for games. I don't think that we definitely set out to say that that is something we think that could be removed. We think actually the ML agents can actually work alongside your QA teams. Like for example, if you can, instead of having, let's say a QA tester do sort of, low-level activities just running around the game, maybe the agent can do that. and maybe if it finds certain things, that maybe the human tester goes in and kind of takes a look. One of the things about machine learning, especially in the context of ML agents, is that if an agent finds a very difficult part of a game, or if it finds a rough spot, that's just like identifying it. A human still needs to go in and actually figure out if this is good, if this is bad, this is intentional. So in a lot of ways, we think this is actually a tool that QA and testing could use to actually make their workflows much faster. And so instead of, what we always hear is that QA is kind of the last thing that kind of happens. Everything is about design, getting it all pretty, get it to compile, getting it to build, and the QA kind of happens if you have enough time. So we also think that because there's always a time crunch in QA, some of these kind of tools and solutions can actually make QA a little bit faster, a little bit more efficient. And so we don't think that removing QA from the workflow is our intention. We actually think these tools can help QA testers do their job. Can you make, let's see, is there any plan to share ML agents example by using other deep learning frameworks such as PyTorch? So that's a great question. So one of the things that we kind of set up ML agents to actually work with, all we have really built is like a Python. We have a Python API that if you wanted to use PyTorch or something else, you could definitely do it. Now it will take a little bit of work because it's not supported out of the box for ML agents. But as long as you have Python, you have our API that interacts with the game itself, PyTorch could work. Whoever asked that question, actually, if you like, we would love if you contribute to actually adding PyTorch to the project, because we do get asked for that, as well as Keras and some other deep learning frameworks. So I'm not sure who asked that, but a great question. Is it possible to merge different experience data on different devices? I think if I can interpret this question, it may be that can you modify the models? Maybe it has a little bit of a different experience on different devices. Again, at the end of the day, you do get exported out like a TensorFlow model. So if you wanted to change some of the parameters, or always want let's say the brain to take the third or fourth or fifth best decision, those are definitely possible. Again, those are much more advanced topics. And so if you kind of know what you're doing, you understand neural networks and layers and things like that, that's definitely possible. Have you been using ML to develop Unity machine learning inside Unity to test on Unity using? So have we used this kind of stuff on anything inside Unity tech? Yeah, absolutely. We have demo games that we test internally with these things, and a lot of the inspiration of what you see today is just we've experimented with different different kinds of environments. We actually have quite a bit of game developers, former game developers at Unity. So sometimes they see our project, they're like, "Hey, I want to get this to work. Can you help us?" And we kind of work with them, kind of figure out the workflow, how that works. So yeah, absolutely, we do incorporate, some of this with some of the internal projects. We also have, we also do a lot of other machine learning. This is just kind of behavioral topics in machine learning at Unity. Again, we do stuff in machine learning, graphics, and other places. So yeah, I definitely do a lot of stuff internally with machine learning. How do we separate game level using ML agent, AI, enemy? If I understand the question, it's like how do we create enemies instead in the AI and instead of maybe cooperative. Again, it depends on the reward and function. If the reward for an NPC is to, a positive reward would be to, remove the player or shoot the player, then of course that would be the behavior of the NPCs. A lot of this is just driven by what the policies are and what are the rewards for an NPC. Okay, so I think that's all the questions. Again, happy if anybody has any other additional questions. Okay, thank you so much. Appreciate everyone's time.